So at the beginning of the class, we went over equation of state. So remind you that equation of state exemplified by ideal gas law, like PV equals to nRT, or we could also have a van der Waals gas law, which have more complicated mathematical equation, or the equation of state for liquid or solid. But nevertheless, an equation of state gives us relationship between pressure, volume, and temperature, right? Three values that defines a thermodynamic state. And in our derivation, we went over definition of alpha and chi, right? So these are the terms that these are the partial derivatives we need to solve in order to derive the equation of state, right? Because we have three variables, they're interconnected to six partial derivatives, but these six partial derivatives are connected to each other. So at the end of the day, we only need two partial derivatives to give us the relationship between pressure, volume, and temperature, right? Then moving on to the first law of thermodynamics. Now we have state functions. For example, internal energy or enthalpy, right? So these are state functions that are in some kind of relationship with my temperature, pressure, or volume. So in our setup, we typically write internal energy as a function of temperature and volume, and enthalpy as a function of temperature and pressure. That's just a conventional written, because as we were saying, once we know the equation of state, we know what pressure is, right? So temperature and volume will tell you what the pressure is for a pure substance that have the same equation of state. For conventional properties, typically we write internal energy as a function of temperature and volume, enthalpy as a function of temperature and pressure. So now we have the same kind of question we had before. Remember, in the volumetric equation of state, we can write volume as a function of temperature and pressure, and then later on we have alpha and chi. So now we are in the same situation. We want to be able to set up experiment so we can get a relationship between my internal energy with respect to change of temperature and volume and my enthalpy with respect to change of temperature and pressure. So some of the things we already defined, like heat capacities, right? So my isochoric heat capacity is defined as a partial derivative of U over T at constant volume, and my isochoric heat capacity is du over dt at constant volume. My isobaric heat capacity is dH over dt at constant pressure. All right, so these are the heat capacities. But it will be, as we were saying, for these relationships involving like three different variables, we need two partial derivatives to solve for their relationship. So hence, we introduce the Joule-Thomson experiment, in which we're setting up the experiment so that the internal energy or the enthalpy is kept constant. So we have a mean to measure the relative relationship between temperature and volume or temperature and pressure. All right, so before we dive into the math and experimental setup, I want to highlight like why we're doing it. The first question. And now let's look at how do we do it. Like we were saying, we were trying to have two different experiments. One is the Joule experiment, in which we're trying to measure the relationship between temperature and volume while keeping internal energy as a constant. So how do we do that? Now, in this case, we're giving you the experimental setup, and I'll walk you through in why this experimental setup leads to a process in which the internal energy is kept constant. So here's the experimental setup. Now imagine my system contains two different chambers. The left chamber contains some kind of gas. The right chamber is empty or vacuum. All right. And these two chambers are separated by a valve that allows the gas to go through or to permeate through that valve into the empty chamber. And let's say we have a thermometer inside the chamber to measure the temperature of the system. And also both chambers are surrounded by adiabatic wall or adiabatic rigid wall. So what are the information we can get, right? So what I just said are the description of the system. And now let's translate those description of the system into equations or expressions. For example, whenever we see an adiabatic wall, what it tells us is that Q equals to 0. Or in plain English, there is no heat transfer between the system and the surrounding. So that's the heat part. The work part. Now, focusing on the work, thinking about this process, we have an expansion of the gas into vacuum. And this entire chamber is held in with like solid wall. So my system, considering both chambers, gas and vacuum, is doing no work to the surrounding, right? The wall is not moving, right? We're just expanding, slowly expanding the gas into the vacuum. Now in this process, the gas is not doing any work on the surrounding because we have the rigid wall surrounding it. So W also equals to 0. Or the other way to put it, now we're ready to use our first law of thermodynamics, in which we have delta U equals to Q plus W equals to 0. All right. Or with this in hand, we thus defined the Joule coefficient. That is mu J equals to partial derivative of temperature over volume at constant internal energy. So in this case, again, the constant internal energy was achieved by carefully set up the experimental condition. The temperature change can be measured using the thermometer inserted into the chamber, and the change of the volume can be carefully monitored by adjusting the size of the valve that's allow the gas to pass to another side. So here it's like we're setting up this experiment so that we have a mean to measure the partial derivative or the change of temperature over the change of volume at constant internal energy. All right, so back to what we discussed. We were talking about three different variables. We have temperature, we have volume, and we have internal energy. And in this case, as we say, they are interconnected with each other, right? Remember, we have the chain rule that connects these three partial derivatives with respect to each other. So if we write out the chain rule, we can then write out a relationship between Joule coefficient, internal pressure, and also our heat capacity, CV. Right, so for example, we could ask you to write out an expression of internal pressure using our Joule coefficient and the heat capacity CV. And let's try it together, right? So we want an expression of partial derivative of U over V at constant T. And we know that using the chain rule, we can write out du over dv at constant T times dv over dt at constant U times dt over du at constant V. Let me write it clear so it's not ambiguous. And this chain rule gives us -1. So if we're focusing on this first term here, the du over dv at constant t term, then we're moving these two on the right and then flip them. What we end up getting is du over dv at constant t equals to negative dt over dv at constant u times du over dt at constant v. And then using the definition of our Joule coefficient and also our CV, we can write it out as negative mu j times CV. All right. Okay, so this part is the internal energy part. And let's move on to look at the alternative experiment scientists set up, so we're keeping the enthalpy as a constant. Again, the purpose here is to establish a way so we can measure the relative relationship between enthalpy, temperature, and pressure. So now we want to set up the experiment carefully so enthalpy is kept constant. So this time I'm gonna walk you through over the setup of the Joule-Thomson experiment, and then we will use our definition of the terms together to prove that this process is having a delta H equals to 0, or a constant enthalpy process. All right, so step one, let's work out these experimental setup first. So what do we have here? Now, on here, we have an illustration of how this experiment is going by looking at its initial state and final state. Now, in the middle, that's just saying like the experiment is ongoing. This is in between or intermediate state, if you like. And what do we have as a setup? First of all, this entire chamber is surrounded by adiabatic wall, including these pistons. These are all adiabatic. So whatever inside the chamber, it's surrounded by an adiabatic wall. And then we have different pressure on the left-hand side and right-hand side of the chamber applied onto the piston that can move left or right in one dimension. Now, within the chamber, we have a porous plug. So when we say this one is a porous plug, we set it to be a special kind of material that allows the gas to pass through, but only at a very slow rate. So only reversible PV work is allowed in this process. Okay? And then in here, we're manually set P1 to be something larger than P2. So at the initial state, the gas is all in the left chamber, but since P1 is larger than P2, it's gonna slowly move to the right chamber along the process. Okay, so that's all the experimental setup. Now, if you were asked to demonstrate why this process, or to prove why this process is an enthalpically constant process, or enthalpy doesn't change for this process, how do we approach this problem? So let's work on that together. I'm gonna do it on the board, and you can see the worked out version of annotated notes. So for this question, first thing I like to do is to list what are the things we know, right? So what are the things we know? We have our first law of thermodynamics. And I hope people in the back can see my handwriting. Okay. And since it's surrounded by adiabatic wall, we have Q equals to 0. Right? And we're talking about reversible PV works in the process when the gas is slowly passing through that porous middle bar. So we have W reversible equals to negative PdV. All right. And then in here, when we're talking about using the negative PdV, we have effectively two different parts of the total work. Or we can write our total work as the work on the left-hand side plus the work on the right-hand side. Or the other way to put it is when we're looking at the W left, what do we have? We have the piston doing work on the gas, or the surrounding is doing work on the system. Or we can write W left equals to the integral of negative P1 dV. Since P1 is a constant, we're just looking at initial volume and final volume of my left chamber. So in the initial state, my left chamber has volume equals to 1, and in the final state, the volume on the left-hand side becomes 0. So this becomes V1 to 0, or we write it as negative P1 times 0 minus V1, and becomes P1 V1. And it's always nice to check our intuition. This should be a positive number because my piston or my surrounding is doing work on the gas. So this is a positive number, we have it correct. And then we have our work on the right. Right, so my gas is doing work on the piston. Or we can write W right equals to all the same equation, but negative P2 dV. But now the final volume is V2 and initial volume is 0. So that's the V2, 0. That's negative P2 times V2 minus 0. And that is negative P2 V2. All right? Or plug these two back into our original equation. Our total work is P1 V1 minus P2 V2. All right? And next up, we're ready to use our first law of thermodynamics, right? So our delta U equals Q plus W, Q equals to 0, and we have an expression of work. What do we have? So delta U equals to U2 minus U1 equals to P1 V1 minus P2 V2. So moving the 2 with 2, 1 with 1, what we have is U2 plus P2 V2 equals to U1 plus P1 V1. Or by definition, we know that H equals to U plus PV. So we have H2 equals to H1. All right, and then in this process, we can easily imagine having a thermometer inserted in the chamber and measuring the temperature change while we are moving the piston, and thus we define the Joule-Thomson coefficient based on this experiment in which the enthalpy is kept constant. All right. And before we move on, quick question. Is my Joule-Thomson coefficient an extensive or intensive property? Oh, anyone want to take a guess? Raise your hand if you think it's intensive. Raise your hand if you think it's extensive. Okay, so why don't we answer this question? So what is the temperature here? Is it intensive or extensive? Pressure, also intensive, right? So if we go back to the original setup, it's the same kind of idea. We can do this experiment with, well, 1 mole of gas, or 0.1 mole of gas, or 100 mole of gas. The result will be the same, right? We're just measuring the change of temperature and pressure, which are two intensive properties. The enthalpy will be the same, no matter how we kept it. Okay, any questions before we move on to a little bit more math? Okay, well, we're ready to go. So here is the little bit of more math we will be looking at. So let me move the terms a little bit so we can put it on the same page. So this is a chapter end problem coming from your textbook. The first part is derived equation 2.65, and I'm going to give you the equation 2.65 here, which is the partial derivative of h over p at constant t equals to negative Cp mu jt. That's the first part. Second part is asked you to show the relationship between mu jt, your heat capacities, and your Joule coefficient mu j. So remember, going back to our original statement, we have the equation of state that links pressure, volume, and temperature, right? So, and we have our internal energy linked with temperature and volume. So technically speaking, we should be able to link our mu jt with mu j if we have information from the equation of state, like chi in this case. All right, so this is like why do we care about it? And I'm gonna give you a little bit of time working on it, and then we'll work on it on the board together. I have also provided you the useful definition of terms here. So the first part, I hope you all finished. This one should be very straightforward. This is like what we did with the derivation of the relationship of your Joule constant with internal pressure and isochoric heat capacity. Now, when setting up the problem, what I like to do is whenever you see expression like Cp and μJt, just write it out as partial derivatives. We're trying to find a relationship between the partial derivatives listed like 1, 2, 3. Right? So obviously, we only have 3 variables in these partial derivatives. So in here, the h, p, and t are the 3 variables we care about, and they are obviously linked by the chain rule. So in this case, we're just rewriting my chain rule and asking for dH over dP at constant t, moving these 2 terms on the right, and find out, okay, that's just a negative μJt times Cp. All right, that's the first part. I'm gonna keep that top part there because we will be using that for the second part. Do you need more time working on the second part before I start working on it? Okay, so go ahead. I'll wait like 3 more minutes. And keep in mind, we have the hint here. The first step is to take the partial derivative of enthalpy over pressure at constant T. That's in the hint. All right. So in this problem, when we start looking at what we want, right, μJt equals negative V over Cp times this whole thing. And in the first part, we derive that the partial derivative of h over p at constant t equals negative Cp μJt. So the first thing is to move this negative and Cp on the left-hand side, right? So effectively, our problem becomes the negative Cp μJt, just moving this one and the negative to the left, equals to chi times Cv times μj times V minus chi times P times V plus V. All right, that's just moving the terms. And at the same time, we can do this partial derivatives based on enthalpy equals to U plus PV. That's in our hint. So let's do that. What do we have? The partial derivative of U plus PV over dP at constant T. We can write it out as du over dP at constant T plus P times dV over dP at constant T plus V times dP over dP at constant T. This part is just writing like dPV equals to PdV plus VdP. All right, just using the definition that enthalpy equals to U plus PV. And these 2 terms cancel out with each other. And in this part, we have our dV over dP at constant T. And in the question, we have a chi in there. So looking at the definition of our chi, what do we have? Knowing that chi is by definition equals to negative 1 over v times dv over dp at constant t. So this partial derivative, dv over dp at constant t, just equals to negative chi times v. With me so far? So what we have in here, like v and v, these two checked, right? And in here, since this partial derivative just equals to negative chi times v, which is by definition true, given the isothermal compressibility, this negative chi pv term is also checked. All right? And on the left-hand side, this one, negative Cp mu jt, and this term, which is the partial derivative of h over p at constant t, this term is also checked. We did that proof in our first step. All right? So what we left over is trying to prove that these two terms equal to each other. That's the last bit of puzzle we need to solve this problem. All right, so our goal here now becomes to prove the partial derivative of u over p at constant t equals to the isothermal compressibility chi times Cv times mu j times volume. All right, so following what we did in our section 1, whenever we see this kind of expression, we'll just write out each of these terms in their partial derivative form. So this chi term, isothermal compressibility, becomes negative 1 over v times dv over dp at constant t. This Cv term is, well, du over dt at constant v. Mu j is, well, we have the dt over dv at constant u, and our volume is just a volume that stays there. All right? And in here, these two terms obviously are linked by the chain rule. Sorry, I don't like to use obviously. So these two terms, again, we have, remember in the chain rule, whenever we have like three variables connected to each other, right, the three partial derivatives, product equals to negative 1. So this is the same situation, right? So we have the partial derivative du over dt at constant v times dt over dv at constant u times dv over du at constant t equals to negative 1. All right, or the product of these two partial derivatives can be rewrite as the negative of du over dv at constant t. I'm just moving this one to the right and then flip it. So this whole term goes in there. All right, so what does this equation become? Now we have volume will cancel out with the volume. The negative 1 will cancel out with the negative 1. And then we have these two partial derivatives, products of each other. Now these two partial derivatives are both partial derivatives at constant volume. So we can cancel out the dv term on top and on bottom. What we end up having is partial derivative of u over p at constant t. And that's what we're looking for. So it looks like a super long and complicated derivation, but effectively what we are using is just plugging definition of these terms in their partial derivative format, right? And using the chain rule, we used it 2 times. This is the first time, that's the first time we use it. This is the second time we use it. And that's about it. It's not hard, it's just need a little bit practice to get familiar with how to set up this question. Okay, how do we feel? And again, back to our purpose, like what we want to do is we scientists like to take as little measurement as possible and to build links between these functions, right? In this case, we're trying to say, can we have a general relationship between mu jt and mu j using like heat capacities and equation of state? In our last lecture, we did our derivation for a general situation, like what is the relationship between your isobaric heat capacity Cp and the isochoric heat capacity Cb. So thermodynamics is a course that we're always talking about relationship between different properties and different functions. Okay, so any question before we move on? All right, sounds good. I have the more like straightforward to follow, I hope, in the annotated notes, derivation of all the problem we work together. So, well, you're here, but for people who are not here and watch the recording, refer to the lecture note. Okay, so go to let's move on to lecture 6 and 7. So this is the handout that I just gave you. Please keep it. We will be using it in our next lecture as well. So in this part, we're talking about application of the first law of thermodynamics. So now instead of looking at the relationship or the fundamental equations, linking them together, now let's move on to look at specific scenarios and see how do we use the first law of thermodynamics to actually calculate properties we care about. Right, so getting started, we'll first talk about the first law and perfect gas or ideal gas. It's the same idea. Again, when we're talking about a substance, we need the equation of state to define what is the thermodynamic state of that material, right, of that substance. And in addition to the equation of state, we need additional information, like in this case, heat capacities, or how does it change with respect to volume. So these are additional relationships. So we have 2 sets of relationships. The first set, again, P, V, and T defines the thermodynamic state. We need a second set that link our internal energy or enthalpy with respect to change of temperature and volume or pressure. All right, so 2 sets of relationships. Now for ideal gas or perfect gases, what we have equation of state is PV equals nRT, and we know for perfect gases, our change of internal energy with respect to volume at constant temperature equals to 0. Or the other way to put it is that for perfect gases, our internal energy, U, is only a function of temperature. All right. And then we're going to use this information to do something that we already did in our last lecture, which is to solve for a relationship between Cp and Cv, and we'll see they match each other. Like in this case, since we know internal energy and enthalpy for perfect gas is only a function of temperature, we can rewrite the definition of heat capacities. Like my isochoric heat capacity, which is a partial derivative of U over T at constant V. Now it's independent from volume. For ideal gases, we can rewrite it as a normal differential, which is du over dt. Or you can put it as du equals to Cv dt for perfect gas. Right. Likewise, we can write the isobaric heat capacity as Cp equals to dH over dt at constant P, rewrite it as a normal differential dH over dt. Or we can say dH equals to Cp dt for perfect gases. All right. And now let's use these two definitions and also like definition of enthalpy, which is U plus PV, to solve for Cp minus Cv. So whenever we have these, let's plug in their differential form. So that equals to dH over dt minus du over dt. H equals to U plus PV, and ideal gases, we have PV equals to nRT, right? So H effectively equals to U plus nRT for ideal gases. So rewrite it as du over dt plus b nRT over dt minus du over dt. Now then it becomes quite obvious to solve for this differential equation equals to nR. All right, so that's the same result we get by solving the more general relationship between Cp and Cv and then using the ideal gas law. So this is a good example that in thermodynamics, very often we will get the same answer using different approaches to solve the problem. And then moving on to more specific examples, again, refresh our memory on the first law of thermodynamics. What we're saying is that the internal energy of an isolated system is conserved, right? So the differential, the infinitesimal change of internal energy equals to the infinitesimal change of heat plus work. So this is just generally true for closed isolated system or closed system. And then on top of that, we have something that is specific. So for example, for du, we know that du equals to Cv dt. That's something we just go over for perfect gases or ideal gases. And then in here, we also have the dW. Let's see, we have a reversible process. We have WREV equals to negative PdV. So here I want to pause and emphasize this once more. Some of the equations are generally true. So for example, if we write du equals to dq plus dw, this is more or less generally true whenever we have a closed system at rest, no external field, right? That's our first law of thermodynamics. It's very generally applicable. But there are other equations that's only applicable to specific process or material. For example, in this case, we can only use W reversible equals to negative PdV for reversible process or a very slow process. All right. Or in addition, we can only use du equals to Cv dt for ideal gases. Now, the common mistake people make in this class is to assume everything as ideal gas. Just keep in mind, if we didn't specify our system being an ideal gas, do not use the ideal gas law. We will specify our system to whether or not it is an ideal gas. If we didn't say it is an ideal gas, you cannot assume it to be an ideal gas. Right? That's a very common mistake people make in this class. Now, if we say, hey, now we have ideal gas and reversible process, and then we can rewrite our equation to Cv dt equals to dq minus PdV, but for reversible PV work, closed system, and also ideal gas. Right, so these are the things that need to be there so that this equation is true. Like, for example, if I give you a true and false problem and say, hey, we can always calculate, this equation is always true, well, then it becomes a false statement because it is only true for reversible PV work, closed system, ideal gas. All right. Then moving on, using what we just learned, we can solve for a specific question. Now, this is the example 2.4 in your textbook. We will set up the problem together, but you can practice it on yourself and let us know if you have any questions, because I probably will run out of time finishing this problem with you. But let's set it up together. So looking at this problem, when we're reading the problem, it says suppose 0.1 mole of a perfect gas. So I want to highlight my perfect gas and write out whatever we know about the perfect gas, right? So PV equals nRT, the molar isobaric heat capacity equals to the molar isochoric heat capacity plus R, heat constant. And also the internal energy is only a function of T, the enthalpy is only a function of T, right? So these are the things we know. Like we know what CVM is, and it's telling us our CVM is a constant independent of temperature. So we can treat it as a constant. All right. And then it's telling us this cycle, this perfect gas, undergoes this cycle, which is a reversible cyclic process going from 1 to 2 to 3 to 4 to 1. All right, so it's a reversible cyclic process. And in this case, when we're reading reversible cyclic process, we can instantaneously write out, okay, it's reversible, so I can use dW reversible equals to negative PdV. And also, because it is cyclic, my delta U of the entire cycle must add up to be 0. All right, so these are the things I will write up when reading the problem alongside. And then we're ready to set up the question. Now it's asking us to calculate heat, work, and delta U for every step and the entire cycle. So let's take the second step, which is the 2 to 3 step, for example. I went over the 1 to 2 in my 9 a.m. session. So let's focusing on this one. So in the step 2 to 3, now we read it. This one is isobaric at constant pressure. So at constant pressure, we want to use our isobaric heat capacity, Cp. So my CPM equals to CVM plus R, which is 2.5 R, or Cp equals to 2.5 NR, right? This is the molar heat capacity. That's just a heat capacity divided by the number of moles. And we know that P2 equals to P3 equals to 3.00 atm. My V2 equals to 1000 cm cube. V3 equals to 2000 cm cube. So we have enough information now to solve for my work, heat, and delta U. Right, so my work, reversible from 2 to 3, well, equal to, well, final minus initial, V3 go to V2 negative PdV. Right, pressure is a constant. It's just plugging numbers to get a result. Similarly, we can solve for our Q, 2 to 3. That gives us, well, T2, T3, Cp, dt, and we can plug in the number because Cp is a constant. We're just looking at the temperature difference. So we're looking at Cp times T3 minus T2. But we don't know temperature from this diagram, but we can easily solve it using PV equals to nRT, or my T equals to PV equals to NR, right? So that's pretty straightforward to just plug in numbers and solve for temperature. And then you can get a number, you can do the delta U 2 to 3 by writing out that as the work plus heat. all right? And this is a very nice point that you can check, because we know that you can either calculate your delta U equals to like work plus heat. You can also calculate delta U by using the equation like du equals to Cv dt. Because remember, we're talking about ideal gas. So my internal energy only depends on temperature, and you can write out du equals to Cv dt for ideal gases. So these two will give you the same result, or the delta U equals to the integral of Cv dt. These two will give you the same result. So you can check your answer to see whether or not you get the correct one. Or after you do the entire cycle, make sure to check that delta U ends up vanish to be 0, because for cyclic process, delta U should vanish to be 0. All right. So work out this problem, because there's more things alongside with it. And sorry, we will pick up on this part, which is the isothermal expansion of gas in our next Monday. So keep your handout. We will be using that.